Good evening, everyone. Myself, Rachit neema, IT-2K24-71. Today, I'm going to present solution for internal test 1 for the subject Numerical Analysis and Design, taught by our professor Shaligram Prajapat, sir. Let's start with the first question. The first question states that solve system of equation. We have two equations, ax plus by equals to c and bx plus qy equals to r, and we have different cases accordingly. We have to solve these two equations, these two system of equation for each cases and evaluate the results. So let's start. Uh, we will use we will use Cram's rules for both of the equation. The algorithm states that we have to take input all the variables, all the inputs, and have to calculate determinant. How we calculate the determinant? Determinant is computed by the formula A into Q minus B into P. It's the cross product. We evaluate determinant and determine the value of determinant could be either 0 or not equal to 0. If determinant equals to 0, that means no unique solution exists for these both equation, and we will stop the algorithm and terminate the question. If d is not equal to 0, then we further proceed and calculate dx and dy respectively and calculate x and y. X and y are the inputs, are the roots of our equation. We will certainly have three cases, case 1 and 2. In case 1 and 2, the value of our q input is changed by just 0.001. This even a tiny change in the coefficient causes noticeable shift in our um, equations. This is a ill condition. The system is sensitive for the variables. Then in case 3 and 4, we have x and y values interchanges. These interchanges may not affect but maybe affect numerical stability. Let's move on to the next question. The next question we have is quadratic equation x square plus 2x minus 2 equal to 0. We have to solve this equation where a equals to 1, b equals to 2, and c equals to minus 2. We have two cases to solve this. The first, to solve this quadratic equation, we will need to find determinant. Determinant we're going to find by the simple quadratic formula b square minus 4ac divided by 2, 2a, which will result in us to getting r determinant equals to 12. We will add under root of 12 equals to 3.4641 for the four Mentisas digit. Uh, Now we will apply these d to calculate to evaluate the roots of the equation in the case 1 and case 2 scenario. For the case 1 scenario, our two roots will be 0.7321 and minus 2.732. If we check, the both are getting 0. And for the case 2, the similar equation but just a switch in order can lead to different root values. For the second case, we are evaluating the value x1 equals to minus 1.366 and x2 equals to 0.3660. We have checked both the roots, and we found with the alternative, with the reordered formula, we are losing the accuracy over the equation and ended up getting wrong answer. This is called claustrophobic cancellation. Here we can see the graphical representation of the following following roots for the same equation shown in the graph. Then we have the third question. We have given a px equals to a n x to the power n plus a n to the n minus 1 x to the power n minus 1 to the a1x plus a0. This is the degree of n to the n plus 1 coefficient. We have to evaluate this equation using brute force method or honors method. We have two different methods and two different approaches. So first we will take brute force method. Force method state multiplying every part of the equation individually. Uh, so we have the formula which we will get the answer n plus 1 divided by 2. We have to add all the n values which will lead to the time complexity of this program to be order of n square, which give us poor efficiency. On the other hand, we have honors method. Honors method takes n directly, and we have addition, which takes the time complexity of on, which is much better than o of n square, which is optimal approach. Honors algorithm states that initializing b of n is equals to a of n, and that recursion calls, which will obtain the quotient. We have taken an example here. We have an equation x square minus 6x square plus 11x minus 6, which is divided by x minus 2, which will give us remainder r equals to 2. And for the every equation, we'll get getting the coefficient, quotient, x square minus 4x plus 3. This is the comparison between brute force and honors method at every point of the values. We have the algorithm for honors algorithm flowchart, in which we take the input array, n input equations, n number of equations, and the remainder. We will initialize b of n equals to a of n and k equals to n minus 1, where k is if equals to 0, then we will continue, or we'll if not, we'll give it the output and stop the algorithm. This is 50% more operatable and efficient in compared to brute force method. The fourth question we are going to have is comparison between iterative roots finding methods. So we have many root finding methods uh, like bisection, falsy position, regular falsy, Newton-Raphson, secant, and fixed point iteration. These all are different methods, but used to evaluate the root of the polynomial, root of the polynomial. For the first, we have bisection method, which calculate m is equals to a plus b divided by 2, which is a midpoint. It is a linear order of conversion. It's a linear. It is good effective method, but it is slow. For a respective, it takes multiple iteration to find out the roots. In some cases, maybe 14 and more than that. The another method for the root calculation, we have regular falsy method. Regular falsy evaluates the root by calculating its slope. So we have the formula for it: a minus f of a, b minus a divided by f of b minus f of a. It also give order of conversion 1. It always convert and give us the root of the given polynomial. Um, but it is faster than bisection, but still slow. If bisection takes 14 iteration to find a root, falsy will take approx 8 or 10 iteration to find the same equation root. Then we have Newton-Raphson method. Newton-Raphson method follows quadratic order of 2, which will give such as x1 is equals to x0 minus f of x divided by f dash of x. Here f dash of x0 is derivative of f of x. It may divert, may not divert. It's not confirmed. It is if our initial guess is right, or a good guess, then definitely we will get the root of the polynomial very fast. But if the initial guess is wrong, we will may not be diverged and not found the root of the polynomial. And we have secant method. Secant method is more like regular falsy method, but it gets to we have to take two initial guesses. It is fast, but not fast as Newton-Raphson. It may or may not diverge the root of the polynomial. For this, we use x2 equals to x1 minus f of x1 minus x0 divided by f of x minus f of 0, f x0. And at last, we have fixed point iteration method, in which we use this is use linear order of one conversion method. It converts only if the g of x is less than, if the mod of g of x is less than 1. It's not guaranteed, and it's Reliability summary, we have the summary is bisection and regular falsy will always give the diversion. But Newton-Raphson is fast, but if only if the initial guess is good. And at last we have secant and point iteration, which may or may not may fail in the long conversion. Here we have the comparison graph for all the iterative methods. The red line showcase the bisection, the green showcase the Newton-Raphson method, and the blue showcase the secant. Here we take an example of x square minus x square minus 2 for the under root of x equals to 1.4142. This is given, and when we apply this, we will find out that bisection take 5 iteration to ended up finding the root, whereas C can take only one or two, three roots to find the conversion. And on the other hand, Newton-Raphson method just take 2 iteration to find out the roots. The best practice is always start with bisection to find the brackets and then switch to Newton-Raphson for fast conversion. Then we have at last question for floating point, associative and distributive law. Here we have to solve. Here we have to solve the system of equation. We have LHS and RHS, which is a plus b minus c and a minus c plus b. Um, we have to prove the associative law. Associative law state that a plus b minus c is not equal to a minus c plus b. Here the order of the equation is changed, but if we when we change the order, we ended up getting different results. So for this we have a equals to 0.5665 e1, b equals to 0.5556 e minus 1, and c equals to 0.5644 e1. Now we calculate and evaluate the calculation for LHS. After substituting the value for ABC, we will ended up getting 0.0770 as the result of LHS, and by substituting the value in RHS, we are ended up getting 0.07656. Here we can clearly see that both are the same variables, but in the different order, does not giving the exact same result. Here the error is occurred. We have take another another example of distributive law which state that a into b minus c is not equal to ab minus ac. For this respective value, when we substitute in that, we will get LHS equals to 0.000555 and RHS equals to 0.00600, which is also not equal, and it states that distributive law also have an error if the position is changed. Here we can see graphically these flaws, these failures in computer may occur by this three errors, like rounding off the mentisas and remove the significant value. We have claustrophobic cancellation, subtracting near equal values and lost the significant digit, for example AB minus AC. And we have representation error. Not all decimal have exact binary representation like 0 1. So this is the graph.